We're finally ready to talk about transformations. We'll look in this lecture at the standard and transformations, rotation, scaling, shear. Uh, then we'll see how we implement them within WebGL. Um, I try to break this lecture up into smaller parts, but it just didn't break very easily. So feel free to take a break anywhere in the middle of this lecture. But what we're going to do here is I want to talk about the standard transformations, but I'm going to talk about them using homogeneous coordinates, and I'll give you a little more justification about why we need homogeneous coordinates to do this efficiently, and then our strategy will be if we want to build up some arbitrary transformation that we might use in an application, it's easier to build them up from simpler transformations. And one of the arguments for that is that when we get a transformation and we actually apply it, we're going to load that transformation into the shader, and the shader will process perhaps millions of vertices using that transformation. So the time it took us to compute that transformation really doesn't matter, because once we have it, it's in there, and we just use it over and over again. And it's often easier to conceptually, if you're going to do some sort of transformation, to build it up in small steps, and then you're going to see that process multiple times as we go through the next bunch of lectures. Now, in general, we can talk about a transformation of a point to a point, or of a vector to another vector. We can think of transformations that convert points to vectors or vectors to points. We're not going to worry about that. We're going to only worry about transformations that will convert a point to a point, or a vector to another vector. We're also going to have some other restrictions, one of which is that these are single valued, that if I transform a point, it's going to give me exactly one other point. And then there's a separate question of, if I look at this point P being transformed to Q, if I have Q, can I get back to P? That's a different issue, and often will not, as we've seen with projections, and many points will project into a single point, so I can't easily go backwards. But we'll see that. Now, the problem here is that what we don't like about this general transformation is that if I want to transform this curve into this other curve, the blue curve into the black curve, if the transformation is really complicated and nonlinear, I would have to transform every point along here, or at least a lot of points, connect them with short line segments in here. What happens with a linear transformation or an affine transformation, the ones we really care about, is because, as we said at the end of the last lecture, is that because they preserve lines, that all I have to do is transform any 2 points on the line, and then I can reconstruct the transformed line instead of having to transform many points. And that's why it's so important in computer graphics to try and at least approximate with affine transforms, even if you have some sort of a nonlinear problem. Okay, but let's turn, we're just going to look for a while at affine transformations. As we said, they're line preserving, and they characterize them. If I said to you, what are the transformations that you normally see in the real world, or in some physical problem, they're going to be rotation, translation, and scaling. Now, the rotation and translation are called rigid body transformations, because if you start with a solid body and you rotate it, you don't really change anything about that body. All of the relationships on that body are the same. Same thing in translation. If I pick up an object and I move it somewhere else, I'm not changing anything about that object, although rotation and translation are going to tell me exactly where that object is once I've rotated it or translated it. Now, the other two really important transformations, are scaling and shear, do in fact change the properties of that object. So, for example, if I scale something to make it bigger, longer in one direction and shorter in another, or uniformly larger or smaller, I've changed that object, and that still will be an affine transformation, but it will not be a rigid body transformation. Shear is when you take something and you do something like pull the top in one direction and the bottom in the other. Suppose you have, think of you start with a square and you move the top to the right and you move the bottom to the left, you get a little parallel pipet. That's a shearing kind of operation, and we can carry that on to objects that have volume or are three-dimensional objects. And it turns out that's an important transformation, although I'll show you at some point how we can get that out of a rotation, translation, and scaling. And again, the importance here is that all I have to worry about if these are the transformations I'm working with is the endpoint of line segments, and that means I can carry them out within the shaders. Okay, so here's how we want to do this is that we start with vertices, we go into here, this transformation will be done typically in the vertex shader, although we can do some transformations we'll see later in the fragment shader. But for the most part, we're going to transform in the vertex shader. We load that transformation matrix from the application as a uniform variable, which we'll see, and then we transform the points. They go off to the rasterizer, and because they're affine, the rasterizer can take the transformed endpoints and generate the triangles or line segments as needed. So vertices go to vertices with the transformation, then in the rasterizer we'll generate fragments or pixels. Now, just a little about notation. Now, at this point, we're going to be working primarily with rotations, representations. But at times I want to be a little more general. So when we're talking about sort of the abstract geometric entity without any representation, I'll use uppercase letters but not bold. And the same with vectors, I'll use lowercase but non-bold letters. Scalars will just be use Greek letters for. Now, if I'm talking about representations, then points will be bold-faced Roman characters PQR, so I can distinguish them from their abstract representation without representation. And likewise, I'll use bold for the representation of points. And since we're using homogeneous coordinates, both points and vectors get represented in the same way, so there shouldn't be any confusion between PQ and R and UVW, although I'll tend to use UVWs for representation. Actually, I'll probably do it the other way. These are representations of vectors, not of points usually, so I should change that word in there. Okay, so let's look at translation. And first we'll look at it in an affine space, and then we'll talk about what does that mean in terms of representations. And we'll do that with the other standard transformations. Okay, so translation is called, say, displacement, just says you're going to move something to another position. Now, one thing to be clear about is that if I'm going to move a point to another point, I give you those 2 points, there's lots of ways to get from here to there, even if they're all linear. I could rotate in some way to get this point over to this other location. I could scale something to get it over here, scale in the proper way. But when I'm talking about an object, and I'm talking about multiple vertices that define that object, there's generally going to be only one way that will get all of the vertices to where I want. So what I'm saying is, if I have, say, that this is one point on, say, a cube, and I translate that cube, even though a rotation might get this particular point over here, a rotation is not going to get all the points to the same place as would a displacement or a translation. So it should be clear from the application which one you're really trying to do. So let's talk about translation. And you say, well, that one should be easy because all I need to define a unique transformation is a vector D that says how far are you going to displace me, that's the length of D, and the direction of D is going to say what direction do I do the displacement. So it looks like if you were able to say, okay, I'm going to represent P by just an alpha beta, an alpha 1, an alpha 2, alpha 3, I can do it in three space and say, okay, and first it has 3 degrees of freedom because it takes me 3 constants or parameters to give you a unique D, and then I can say, well, why don't you just use
point vector addition in 3 dimensions and say that all of the new points are given by the old points by just adding on this displacement vector, and we know a point plus a vector yields another point. Well, it turns out that's the one, even though it's the most simple one conceptually and simple to write down this way, this is the one that's the biggest problem, as we'll see in a few minutes. Okay, so here's again the point that if you're going to translate a whole object like this cube, there's really only one way to do it. And I think there's some exercises in the notes that say what's the minimum number of points to determine in 2 and 3 dimensions a unique translation, and I think that's a good exercise to try. Now, let's drop that abstract view and look at, say, okay, but what we're really going to use is some sort of representation. So now let's go to the representation in homogeneous coordinates of our points and see how we can do a translation or displacement. Okay, so let's say I have a point, and now not a vector, but a point, x, y, z, 1, because it's a point, and I'm going to translate it to x prime, y prime, z prime, 1, because that's going to be a point, using a vector who has a representation dx, dy, dz, and a 0. Now, there's a couple of neat things here, is that if you just algebraically do this, just say, I add p and d to give me p prime, I get these 3 equations. It says x plus dx, y plus dy, z plus dz. And notice that 1 plus 0 gives me a 1, so it still says, oh, that has to be a point. And that's kind of a good check on what you're doing if you're doing some complex operations. If I add two representations of vectors, the 0 in the 4th component, and the 0 always gives me another vector of 0. If I try and add 2 points together, notice what happens. I get 1 plus 1, which is 2, and I say that doesn't make any sense because all I can have is a 0 or 1 here, a 0 for a vector and a 1 for a point. So there's some nice sort of checks built into this in homogeneous coordinates when you just try and do the very straightforward algebra. But this says, okay, but here's again just essentially what we said back here, which is that the new point abstractly is the old point plus some vector, and when we do it using representations, I get these 3 equations. Now the problem here is this is saying, as we just saw, that you get a new point by adding a point plus a vector. The problem with that is it doesn't work with the other operations. And so I want a matrix way of doing it that says, in order to get p prime, the new point, I want to multiply by some matrix to give me, given p, I want to multiply by some matrix based on d that's going to give me the new point p prime. Well, turns out if you stay with 3 by 3 matrices, there's absolutely no way to do that. You can try that, you can fool around with it, it's not going to work. You can't do it in a 3 space. But if you go to 4 dimensions, you can find a matrix that you can multiply p by, based on d, you'll see in a second, and that will give me p prime in homogeneous coordinates. So that's one of the reasons it's called the big trick. We converted a vector addition or a point vector addition in 3 dimensions to a matrix vector multiplication in 4 dimensions. And that is what's going to make everything work. Okay, so here's the matrix that we're talking about. It says if you have that representation, then look at this matrix. It's got 1s down the diagonal and the displacement components are over here on the right. So look at what happens when I multiply this by the representation of p. So it would be multiplying it by a column matrix x, y, z, 1. X times, so the first component of the result would be x times 1, which is just x, 0 times y, 0 times z, plus dx times 1, because that was a point. So it just says the new x is the old x plus dx, which is precisely the first equation of translation. Likewise, if I multiply x, y, z, 1 by the second row, 0 times x, 1 times y, 0 times z plus 1 times dy, I get y prime is y plus dy. Likewise, z prime is the new z is z plus dz, which are exactly the equations that I want. And the last row says x gets multiplied by 0, y gets multiplied by 0, z gets multiplied by 0, 1 multiplies 1, and it leaves the fourth component as 1. So this is perfect. This is exactly what I wanted. I go to 4 dimensions, no big deal, because I'm going to build this into hardware anyway. So it doesn't matter that I went from a 3D problem to a 2D problem. And the true advantage you're going to see is when we start combining translations with rotations and scalings in just a little bit. Okay, now let's get to rotation. How would you define a rotation? Well, there's a couple of ways I could do this. Let me do this probably the way that you've seen this when you dealt with Cartesian coordinates in high school. If I rotate xy to a new point, x prime, y prime in 2 dimensions, how do I do that? Well, one way to do this is to convert everything to polar coordinates and say, okay, what have you done by rotation? You've kept the radius the same, and all you've done is change the angle that this line makes with the axis. So if I do it in polar coordinates, I've increased the original angle phi, that was the angle that the first point makes, by theta, so I can write it this way. The new x, now converting back to rectangular coordinates, rectilinear coordinates, I get the new x, this is x prime, the new x, this should be x prime, y prime, was the old x. What was the old x? The old x was r cosine phi, but I've added an angle theta to it, and the new y is r sine theta plus phi, because I've added theta to the angle. Now, if you go back to your high school trigonometry, you can expand this out. The cosine of the sum of 2 angles is cosine minus sine, and sine of theta of the sum of 2 angles is sine cosine plus cosine sine. If you use that in here, you'll recognize that r cosine phi is the original x, r sine phi is the original y. Substitute that back in, and you get these two equations for x prime and y prime. So the new x is the old x times the cosine of the angle minus y times the sine of the angle, likewise for y prime. So it's a very simple 2-dimensional rotation. Also notice there's going to be a rule here we're going to see more in 3D, is notice we're measuring the angles this way. There's what's called a right-handed rule for defining what a positive angle is, and we'll come back to that when we look more at 3D. Now, one thing you say is, what if this were 3D? What if this is a picture in 3D and we said, oh yeah, 2D is a special case of 3D where we look at the plane z equals 0. So if now we say, okay, well, that means there's a z-axis coming out in this direction, and what's happening with the z's when we do this kind of a rotation? And the answer is absolutely nothing. That when I do this kind of a rotation, all the xy's maintain their z's. So if this was the same kind of rotation but in another plane of constant z, that value of z would remain unchanged. So in fact, this 2D rotation is really a very special case of a 3D rotation, which is what we see here. It says that you're rotating in planes of constant z, so the equation for the new x, the new y, the new z is given by the two equations we had before, plus the equation that z doesn't change. Now, I really want to do this in homogeneous coordinates, so I also want to add on the statement or an equation that says, well, the w, the fourth component, if it was 1, it's going to stay there as 1. Notice that if you think about this, that you can rotate vectors, and this will apply to vectors, so you could say the w prime is the old w, and it would work whether it was the w was 0 or 1. But let's look at what's the resulting matrix now we get that gives me a rotation about the z-axis by an angle theta. And that's all right here. It's this nice little 4x4 matrix, which gives you exactly the equations we just had. If I multiply this by the column x, y, z, 1, I get for the new x cosine theta minus y sine theta. The new y is y sine plus x cosine. Z is unchanged, and the W component is unchanged. So that's our first rotation. Now what about if I just sort of change the names of the axis and swap around the X and the Y and the Z axes, I can argue the same way. If I rotate about the X-axis, the X values are unchanged, and the Y and Z change exactly as they did for the case of rotation about the Z-axis, but the entries go in different places in this matrix. And if you do this carefully, you get the following two matrices. You have to be a little, the only little part you have to be careful about is where this sign goes, whether the minus goes here or it goes here, or whether the minus goes here or up here, and this is correct. Let me tell you what the basic rule is. The basic rule is called the right-hand rule. If you look down the positive z-axis back towards the origin, that a positive rotation is counterclockwise. So if you wanted to know what was the positive direction of an x rotation, you would look down the x-axis from the positive side and say it was going in a counterclockwise direction with the y and the z values. And that's what will determine these signs correctly for you. Okay, so there's the second one. We now have a rotation matrix separately for x, y, and z, and we're going to build up from these separate rotations to a general rotation, which says, well, what if I had an arbitrary axis in space and I wanted to rotate my object about that arbitrary axis? Well, this is our strategy. We're going to start with the simple rotations and combine them carefully to get the rotation that we want. Okay, let's move on to scaling. In some ways, scaling is the easiest one. Let me mention one more thing, because this will be true for scaling too. For every rotation, we're going to use this. Let me come back to this one, back here. For every rotation, there's one point that will not change, and that's called the fixed point of the rotation. Here it's the origin. In fact, it's the origin the way we've defined the z rotations, the y and the x rotations. We have a fixed point of the origin. So the correct statement would be, these are the matrices for rotating about the x, y, and z axes with a fixed point of the origin. So the question we want to answer eventually is, what happens if I want to rotate about an arbitrary vector in space where the fixed point is not necessarily the origin? Okay, so that's where we're going. Okay, but first let's do a few other things. So what about scaling? Well, scaling with a positive scaling constant makes things longer in that direction. If the constant is between 0 and 1, it makes it shorter in that direction. So we can talk about having separate, oh boy, there's another little mistake, separate x, y, and z rotation. So this should say x prime is sx times x, y prime is sy times y, and z prime is sz times z. And that's, if you translate that to a homogeneous coordinate representation, it's pretty simple. It's just putting sx, sy, and sz on the diagonal. And again, we don't want to change the w component. This again, there's a fixed point here. Both rotation and translation have a fixed point, and the fixed point is again the origin. That if you apply this to 0, 0, 0, you get 0, 0, 0. So every scaling has a fixed point, and you could think about what things would look like if you had the fixed point somewhere else. Which we might want to do. Suppose this is an object out in space, and I don't want to scale it from the origin, which say is over here somewhere. I want to scale it from the middle of the object and have the fixed point over there. Now, also notice from these diagrams, we have no reason to want to scale equally in all directions, which would be called uniform scaling. So these three constants can be different. One could be large and the other small, or we can get something like this. Now, what happens if one of them is negative? Well, I think we've seen this a little bit before. You get reflection about that axis. So simple picture of that is if here's just using 2 dimensions and letting the constant, all the combinations of 1 and -1, so you can flip about one of the axes, or you can flip about both of the axes as over here. So reflection is just a special case of scaling, and if we combine scaling and reflection, then we have constants that could be negative and can have any magnitude, and so we could stretch it or shrink it and reflect it too. That's pretty straightforward. Now, what about inverses? What about the inverse matrices of these things? What if I want to translate and then translate it back, or rotate and rotate it back? Well, you have two possible strategies. One is you could actually compute the inverse matrices symbolically using Mathematica or MATLAB or something, but it's much easier to just argue on physical grounds and say, well, look, if I translated something by a vector d with components dx, dy, dz, what I should want to do to get back, which is the inverse matrix, is just go in the opposite direction and change the signs to minus dx, minus dy, minus dz. So that's simple, and if you look at that, and that's a translation matrix. So the inverse of a translation is another translation. And if you actually multiply the two out, you'll get the identity matrix. Likewise with rotation. If you rotate a matrix by an angle theta, then if you want to get back to where you were, you use minus theta. But there's another neat little thing that happens, is if you look at the rotation matrices, all of them have the cosines on the diagonal and the sine terms on the off diagonal. And from basic trigonometry, we know cosine is symmetric about the origin, and so cosine of minus theta is cosine of theta is the same, and so all the diagonal terms don't change. And what happens to the off diagonal terms? Well, sine flips. That sine of minus theta is minus sine theta. So what does that do? It transposes the matrix. So for every rotation matrix, and this will hold for any product of rotation matrices, that if you want the inverse of a translation matrix, you can either negate the angle or you can just take its transpose. Those are the same operations. Now scaling, again, it's pretty obvious. If you make something longer by a factor of 2, you want to undo it, you do it by a factor of a half. So you just change the three scaling constants to 1 over, each one to 1 over what it was before. Okay, so that one is pretty easy. And notice too that you can, for scaling, get non-invertible matrices. If you scale by a factor, any of those is 0, you get 1 over 0, and that says you can't undo that. So that's built into that. Okay, so now we have the basic matrices other than shear, which we'll come to a little later. And now we want to look at what happens when I multiply them together, or the word mathematically is I concatenate those matrices together. So one of the things you can first argue kind of inductively is that if I take an affine matrix and I multiply another affine matrix by another matrix, which is also affine, the result is affine. So if I have a matrix that preserves lines, or apply a transformation that preserves the lines, and apply another transformation which preserves lines, then the combined transformation preserves lines. Physically, when I argue it in physical grounds, that's pretty obvious, but you can prove it mathematically if you like. Our other thing is what happens about how much work it is when you multiply a bunch of matrices together, because this is our argument that well, I want to form things by little or form things from simple matrices that I know that are all going to be 4 by 4, and I'm going to multiply them all together. But again, I want to just repeat the point I made. If you're going to apply it to a lot of vertices, then the trick is to form it no matter how many it takes, A, B, C, A, B, C, D, A, B, C, D, E, F, and then just use the product, send that to the shader, and just use that shader. But the hard part, as we note here, is going to be how do I form the matrix that I want from the specifications that come from the application. Okay, a couple of notes about the order of transformations, because this is going to affect your programs, and you start by getting it backwards usually, because the transforms actually get applied backwards, and you'll probably think they're being applied forward. So let's consider the following. Suppose I consider a matrix ABC made up of three matrices multiplied together that then gets applied to a point P. Now we're assuming here that P is represented by a column, or a column matrix, and these are square 4 by 4 matrices, and so the mathematics all works out. Now you could apply the parentheses any way you want. What we said in the last slide is what you're going to do is you're going to form ABC and put it together probably in a single matrix. But suppose you look at it this way just for a second, that says if I put the parentheses this way, I'll get the same result. But if I multiply C times P, I get a point. I multiply B times that result, I get a point. I multiply A times that result, I get another point. But notice that what's happening in terms of the point is even though you say the matrix ABC, the way, because everything is multiplying on the right, that you're getting actually C is being applied to P first, followed by B being applied to P, and A being applied to P. And unless you're in a language like Arabic or Hebrew, where you read in the other direction, this just doesn't seem right. The natural tendency says, oh, I have the matrix ABC, A is being applied first. No, A is actually being applied last if you're using column matrices to represent your points. Now, some of the original references in computer graphics use row representations for points, and which is equivalent to taking the transpose of everything here. And if you look at that mathematically, then you're multiplying a row times the transpose of these matrices. And now, if this were ABC instead of CBA, now you would be applying them in the order in which you read them from left to right. That was one of the arguments for using this form, but essentially no one uses this form. You might come across it in some older software, but we do these things this way. And generally what this means is if this was in a program, you would define A first, then you would define B, and then you would define C. So sort of the little rule is sort of the last matrix specified is actually the first that's applied. Or think of it, I think I'll have that reference again in a little bit, is that think of it like a stack. You know, that if this were a stack, you would be putting A on the stack, then B on the stack, then C on the stack, and the first one off the top of the stack would be C. And even though you're not doing a physical stack, sometimes it helps computer science people to think of things that way. But generally, I like to think last one specified is the first one applied. Okay, so now let's look at our first example of combining things. And the first one would be, let's suppose that I get an arbitrary rotation, and you'll have to believe me that you can get any rotation you want by a rotation by X, followed by a rotation about Y, followed by a rotation about Z. The hard part is determining what these three angles should be to make that happen. They're called the Euler angles. And we'll talk about how we can derive them from specifications, and there's a long example in the book about doing that. Another point to make here is, remember, rotation matrices don't commute. So AB is not the same as BA. And if the dimensions are different, AB might exist and BA might not. So in terms of what's physically going on, a rotation about X followed by a rotation about Y is not the same as if I did the rotation about Y by the same angle first and then applied the rotation about X. Now, on the other hand, I could do this in a different way. I could say, oh, I want to do the Z last, but I want to do the X after that, before that, and then the Y first. That's possible, but you'll get different theta Y's and theta X's. So any order is possible, but the actual angles you get, the Euler angles, depend on which order you choose for the rotation. So be careful at it. We'll try and stick with X, Y, and Z when we use this form, but any other one is valid. And in fact, you can actually prove to yourselves that you could do X, Y, followed by another X if you choose the angles just right. And you see that in action sometimes if you're playing around with some application where you're doing the rotation by how you move your mouse on a touchpad or a trackpad. Okay, now this says, okay, I can get any rotation I want. All of these have a fixed point of the origin. Now the next step is, what happens if I want a fixed point that's not at the origin? Okay, well, one of the basic rules we're always going to follow is, if I know how to solve a problem, an easy way to solve a more complicated problem is to convert it into the problem I know how to solve. Well, if I know how to solve this problem of doing an arbitrary rotation about the origin, which I almost know how to do and will know soon, if I want a rotation about an arbitrary fixed point, then let's do the following. Let's move the fixed point to the origin. How do I do that? I apply a translation to my object, all the vertices that define that object, by how much? Well, by a vector that's determined by the point where usually that'll be the center of the object, the fixed point. So I do minus that to get it down to the origin. Now I'm assuming I know how to do the rotation here, so I do the rotation. And then, well, wait a minute, it's in the wrong place, so I need to put it back. So I'll do a translation, but translation by what? The negative of what I did to get it back here, which is by PF, the coordinates of this point over here with a 1. Okay, so there's the form of it. It would be a translation, a rotation, followed by the inverse of the first transformation that I did. So there's rotation about an arbitrary point in space. Not quite yet everything, because I haven't told you how do we get this for, if I give you the vector that I want you to rotate about, but we're getting there. It says here's how you can build up something from simpler matrices. Now another variant of that is this, which is called instancing. Because generally when I build models, I build them out of much simpler entities that are located in their own coordinate system, which is generally called modeling coordinates, and they're generally with a nice orientation for that object. So for example, if I was working with cubes or even rectangular, any kind of a rectangular parallelepiped, or what I would do is start with a prototype object that was centered at the origin, and the sides of it were aligned with the x, y, and z axis in a model space. And then what I would do is I would size it to the size I want, orient it the way I wanted, and then move it to where I wanted it to really be. And that's known as the instance transformation, because every time I take the model and I apply that transformation, I'm getting an instance of that prototype object. So here's showing you one starting with a little prototype of this apple. I scale it up to the size I want. I rotate it to get the orientation I want, and then I translate it to be where I really wanted it to be in my world space. Now, one of the things you can try and convince yourselves of is that this, if I do it in any other order, it's going to be much harder to do. That this is the natural way to do it if you assume your objects are centered at the origin with a nice, convenient orientation. You wind up with a lot more transformations if you try and do this. So so if we agree on this, that an instance transformation is a scale followed by a rotation followed by a translation, so we could write I equals T R S for that instance, and then we'll be doing a lot of instancing as we build up our models. Okay, now one last transformation is this question of shear, and let me at least spend a couple of minutes on it ending this lecture. So we said what you do at shear is you pull parallel faces apart. So you can call this x direction shear, where you pull the top to the right, you pull the bottom to the left. You can also do this in the z direction. You can do this in the y direction by pulling this face up and this face. Okay, you might see I've seen a little glitch there where I hit the wrong key. Okay, so back to shear. So I can do that. Notice there's a complex ways I can combine pulling, and if I'm doing X shear, I could pull the top in two different directions. So there's a lot of different ways to do shear. But let's just take this pulling the top to the right and the bottom to the left. If you look at what's happening, none of the Y values are changing and none of the Z values are changing. You're only changing the X values by how much you pull it. So that if this was sort of, all these faces were orthogonal to each other, you can talk about how much shear I did by the new angle that the right side is making with the x-axis. So if you sort of take a side view of that, you get something that looks like this. That an XY on the top, the Z, remember we said the Z's aren't going to change. So this is all in a plane of constant Z. All the Y's are staying the same, but the X's are moving over based on how far I pull it, which can be determined by this angle. And if I work it out, the trigonometric function I want is the cotangent of this angle, and the new x is given as x plus y cotangent, and this is this is in homogeneous coordinate form because the W is not going to change. Here's a 4x4 matrix that does shear. And what about the inverse? Well, that's easy. The cotangent of minus theta is minus cotangent theta. So if I shear in this direction, to undo it, I simply shear by that angle in the opposite direction. So that's another one. So generally, there's a derivation. I think I signed this a problem in the notes of getting this from just rotation, translation, and scaling. You can do that, but it's such a simple form that usually it's easier to say, hey, I'm just going to write a shear matrix, and here's what it looks like. And then you have all the variants of shearing in the other directions to add to that. Okay, but those are our basic matrices that we're going to use throughout the class.